So welcome back to another lesson in MCV4U. Today we'll be looking at evaluating limits, and we'll be looking at a couple of examples based on the understanding of limits that we looked at previously. So we want to start with a warm-up question here. So here it says, given the following function, determine if the limit exists at x is equal to -2 and x is equal to 0. So if you remember previously, we looked at this idea of piecewise notation. And we looked at this piecewise notation where we split these these functions into separate components based on the restrictions that are provided. Okay, so let's take a look at this. So if we look at the limit as x approaches 2 from the left, that means we are subbing it into f of x is equal to -x. So we're subbing in -2, which is -2. That will give us a value of +2 here. So the limit as x approaches 2 from the left of the function f of x is equal to 2. Now let's look at if we look at it from -2 from the right-hand side. So limit as x approaches 2, so from the right, so again, that 2 positive. Get those negatives in there. So as limit as x approaches -2 from the positive side, here we have f of x is equal, and the function that's represented when it is going from the right is -x² plus 6. And if we sub in our value of -2, we'll have -2² plus 6. Here it will be -4 plus 6, which will give us 2. And therefore, we can see that if we write the limit as x approaches -2 for this function, we see that it will be 2, and that's because the left-hand limit and the right-hand limit are equal. So again, when it goes from -2 from the left and -2 from the right, they both give you a value of 2, which means that the limit as x approaches -2 will be 2. Okay, so let's look at also, they want to find when x is equal to 0. So the limit as x approaches 0 from the left, the function that represents that is -x² plus 6. And so -0² plus 6 will give us 6. And if we approach the limit as x approaches 0 from the right, see that f of x is equal to 4. So here we see that the left-hand limit and the right-hand limit do not, the left-hand limit and the right-hand limit are not equal. Therefore, the limit at x as x approaches 0 does not exist. So let's just write that down. So the left-hand limit does not equal the right-hand limit, and therefore the limit as x approaches 0 for f of x does not exist. So again, because that is because the left-hand limit does not equal the right-hand limit. Okay, so let's see how this graph looks. Just draw a graph for yourself on the right-hand side of the page. And so we will go up here. We'll go 1, 2, 3, 4, 5, 6, 7, 8. Same thing on the bottom. 1, 2, 3, 4, 5, 6, 7, 8. Your positive will go 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And so there's a couple features that are happening here. And so we see that at 0, so at 0, remember the limit does not exist because again, there's two values. So let's start with that. So again, at 0, from the left-hand side, so from the left-hand side, it reaches 6, 1, 2, 3, 4, 5, 6. So there's a hole here. And then the limit as x approaches from the right-hand side reaches 4. So 1, 2, 3, 4. And then if we look from the values of -2, so here, again, when x approaches -2 from the left-hand side, it reaches a value of 2. So that would be right here approximately. And then when x approaches 2 from the right-hand side, therefore, you get a value of 2, and then it connects there as well. And this is represented here as -x² plus 6. So that's the semi-parabola here. And this one is represented as -x, which is the linear line here as well. And then lastly, when we look at that, when x is greater or equal to 0, we see that it is equal to 4 from the right-hand side. And it will just be a straight line at 4. Okay. So far, we have examined how to determine the limit of a function for a specific value of the variable x from a graph. More often, however, more often than not, however, limits will need to be determined without having the graph as a reference. Okay, so let's look at this first idea of direct substitution. Okay, so direct substitution, if there is no restrictions, and you can simply just sub in the, so then we can simply just sub in the value that the limit shows up from. So here, we see that the limit as x approaches -3, we can just simply sub that into the equation. So here, we write as 4 over, and x will sub in as -3. So -3 plus 1, which will give us 4 over -2, which gives us -2. This is what is called a finite limit, because here an actual value is provided for us. So again, here, since the limit is being evaluated where the function is continuous. So let's write that down. So since the limit is being evaluated where the function is continuous, then direct substitution works. And if you look at how this graph would look, it would look something like this. So if I draw a graph, like here. This is one. There's that vertical asymptote here. And the graph looks something like this. Here we see that at -3, there is an actual value that exists here, which would be approximately at that area. So again, since the limit is being evaluated where the function is continuous, then direct substitution works. However, sometimes it's not possible to find the limit of x as x approaches this number or a value by direct substitution. So let's look at the limit here as we have x squared minus 4 over x minus 2 as x approaches 2. Again, so let's look at what happens if we actually try to use direct substitution. So if we try to use direct substitution, we sub the value of 2 in. It's 2 squared minus 4 over 2 minus 2, which gives us 0 over 0. And 0 over 0 is this indeterminate case. It doesn't actually tell us anything about the limit. So here, we're going to look at strategies, again, for solving limits so that we do not get this indeterminate case. So the first strategy that we'll look at is factoring. So here, if we look at this first example, the limit as x approaches 2 for the function x squared plus 4x minus 12 over x squared minus 4. So for factoring here, we'll write the limit as x approaches 2, and we can factor x squared plus 4x minus 12, which give us x plus 6, x minus 2. Again, the bottom is going to be difference of squares, which will give us x plus 2, x minus 2. Here we see that we can cancel out the x minus 2, and this eliminates the indiscriminate case. So sorry, indeterminate, not indiscriminate. So eliminates the indeterminate case of 0 over 0. Here, then we can rewrite this equation as the limit as x approaches 2 for x plus 6 over x plus 2. So here, once you have simplified, the, the restriction, you can use direct substitution, or you can substitute the x value to solve for the limit. Okay, so here we will just sub in our x values. It's 2, so 2 plus 6 over x plus 2. So we'll just write that there. We'll already sub that in. So we have 2 plus 6 over x plus 2. Oh, sorry, over 2 plus 2, which is equal to 8 over 4, which will give you a value of 2. So the limit as x approaches 2 for the equation x squared plus 4x minus 12 over x squared minus 4 will provide you with 2. And so this is a finite limit again. Okay, so let's look at this one here. So the limit as x approaches 2 of x minus 2 over x squared minus 4x plus 4. Here we can write the limit as x approaches 2. At the numerator, we have x minus 2. If we factor the perfect square trinomial at the bottom, it will give us x minus 2 squared. We can cancel out one of these, x minus 2. So here we'll have the limit as x approaches 2, 1 over x minus 2. And so if we sub in the value of 2, so let's move this down here. So if we sub in the value of 2, we get 1 over 2 minus 2, which is equal to 1 over 0. So here we clearly can't have 1 over 0, but what is actually happening here? So if we go from the left-hand side or the right-hand side, so there's two ways to write something that is close to 0. So if we write number really, really small that gets really, really close to 0, so 0.0000001, right? That would be as close as it, and it goes to positive infinity. If we write a number that's also really small, but is negative 0.0000001, that would go to negative infinity. And so if we look at this graph here, if we draw one for ourselves, we see that there will be a vertical asymptote at x is equal to 2. And if we look at that, the limit as x approaches 2 from the left of the function 1 over x minus 2 will be negative infinity. However, the limit as x approaches 2 from the right of 1 over x minus 2 will be positive infinity. And therefore, these two are not the same. So again, we'll write left-hand limit does not equal the right-hand limit. And therefore, the limit as x approaches 2 of f of x does not exist. Okay, and this is what we call infinite limit. Let's look at this last example here of x cubed minus 125 over x minus 5. And so here we see that at the top, it's a difference of cubes. So let's write that out. So here we have the limit as x approaches 5 of x cubed minus 125, which we can rewrite as x minus 5, x squared plus 5x plus 25 over x minus 5. And here, the x minus 5 can cancel out. And here we'll be left with the limit as x approaches 5, x squared plus 5x plus 25. And we can sub in the value of 5 here. Let's give us 5 squared plus 5 times 5 plus 25, which here will give us an answer of 75. And that is still considered a finite limit because it gives us a direct value. Okay, and now let's take a look at this question on expanding. And so here we have 2 plus x to the power of 3. And here we can expand this using Pascal's triangle. So if you remember, when you looked at Pascal's triangle, we had row 0, row 1, row 2, and row 3. Now row 1 started with 1 at the top, row 2, 1, or sorry, row 1 would have, row 0 would have 1, row 1 would have 1 and 1, row 2 is 1, 2, and 1. And here we're looking for row 3, which would be 1, 3, 3, and 1. Remember, this is Pascal's triangle. So here we're looking for the limit as x approaches 0. So remember the first value or the a value. So 2, it will start from the, the largest exponent and then go down to 0. And then so and then the b value, the x value, will start from the lowest exponent and then will increase as well. So here we can write it as the limit as x approaches 0. So the first coefficient would be 1. And we see that our a value will be cubed and our x value will be 0. And we keep doing that. And so again, the 2 decreases by 1, and then the x will increase by 1 until we get the a value to be 0 and the x value to be 3. So second one here, the coefficient is 3, 2 squared x to the power of 1 plus 3, 2 to the power of 1 x to the power of 2, and 1, 2 to the power of 0 x to the power of 3. And then at the end, there's the negative 8, and this is all over x. So if we simplify that, we get the limit as x approaches 0 to be 8 plus 12x plus 6x squared plus x cubed minus 8 divided by x. Here we see that the positive 8 and the negative 8 will cancel out. Once we get that here, we can factor out an x at the top to help us cancel that out. So write the limit as x approaches 0. So factor out the x, and we'll be left with 12 plus 6x plus x squared over x. And so the x values will cancel out here. And now we can simply just sub this into the equation. So we'll sub 0 into the equation, which will give us 12 plus 6 times 0 plus 0 squared, which gives us a value of 12. And that will again be a finite limit. Okay, so let's look at 2 more questions. One we're going to look at using common denominators. And the next one we're going to look at using conjugates to eliminate the radicals. So here, if we look at the common denominator, we know that we have to make the common denominator here of x plus 4 at the top, and then we also have to make it so that the x minus 3 at the bottom can cancel out. So let's take a look at this. So here we have the limit as x approaches 3. And if we rewrite this, let's do some large brackets here. And so if we multiply everything here by x plus 4 as the common denominator, or 7 bracket x plus 4 being the common denominator. So let's just write that down. So the common denominator is 7 bracket x plus 4. So from the first term, multiply that by 7, give us 7 over 7 bracket x plus 4 minus, and here we'll multiply the negative 1 over 7 by x plus 4. So we'll have x plus 4 over 7x plus 4. This is all over x minus 3, which I'll write in a different color. So here, what we want to do is we want to multiply this negative into these components and then rewrite our equation. So here we have the limit as x approaches 3. Now we have 7 minus x minus 4 over 7 bracket x plus 4. And we also have the 1 over x minus 3, which we'll write on the side here. And that's just from the denominator of x minus 3. From there, we can simplify. We know that the limit as x approaches 3, and we'll simplify the top, which would give us negative x plus 3, still over 7x plus 4, and we have 1 over x minus 3. And we can see here, if we factor out a negative from the negative x plus 3, then we'll be able to cancel out the x minus 3 there as well. So if we factor that out, let's rewrite this. So the limit as x approaches 3, let's factor out that negative. We'll have x minus 3 over 7 x plus 4 x minus 3. And so here we can cancel out the x minus 3. And now that we got rid of the restriction, then we can simply sub the values in. So here we'll sub it in. Be negative 1 over 7 bracket 3 plus 4, which will give us a value of negative 1 over 49 for our final answer. So the limit as x approaches 3 of the function 1 over x plus 4 minus 1 over 7 all over x minus 3 is equal to negative 1 over 49. Okay, so the last thing we'll look at here is using conjugates to eliminate radicals. So remember, the conjugate radical is the same binomial terms. So here would be square root x plus 8, but we're switching the sign or the opposite operation. So instead of square root x plus 8 minus 3, we're going to multiply it by square root x plus 8 and plus 3. So let's do that. So multiply the top and the bottom by square root x plus 8 plus 3, and we'll multiply the bottom by the same thing as well. Okay, so let's rewrite this. So here the limit as x approaches 1, so square root x plus 8 minus 3 multiplied by square root x plus 8 plus 3 will give you x plus 8 minus 9. So actually do this in brackets. Just rewrite that actually. So we'll do x plus 8 minus 9 all over x minus 1 square root x plus 8 plus 3. Here we can simplify the top. Look at the limit as x approaches 1. It would be x minus 1 over x minus 1 square root x plus 8 plus 3. Here we can simply cancel out the x minus 1. And now we'll be left with 1 over square root x plus 8 plus 3. And we can just sub in our value. So now here we have 1 over square root x plus 8, which would be 1 plus 8 plus 3. And that gives us 1 over 3 plus 3, which is equal to 1 over 6. And so here we see that the limit as x approaches to 1 for the function square root x plus 8 minus 3 over x minus 1 will equal to 1 over 6.